Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video, another video in our series of videos on set theory, is going to deal with two important types of notation when it comes to representing sets. The first type of notation is what's known as roster notation, and the second type is what's known as set builder notation. The roster notation is actually quite straightforward, so let's just have a look at that first. So the roster notation, the roster notation is where we list the contents of our set, So in relation to roster notation, what we actually do is we list the elements. That's probably the best thing to say rather than the contents. We list the elements of the set under consideration. Under consideration. That should be two words there. Under consideration. So for example, I might say that we have a particular set A, and I might say that A is the set that contains the elements 2, 3, and 5, as an example. Well, when you see a set in this particular fashion, now this is a finite set in the sense that there's a finite number of elements in the set, And when we have a finite set, well, it depends on the size of the set, I suppose, But in this case, the cardinality of this set, there's 3 elements in it, So it has cardinality 3 or has size 3, And what we've done is we've just listed the contents of the set between two curly braces, Or we've listed the elements of the set between two curly braces, and this is what's known as roster notation. I might say something like this, something else. B is equal to Barry, Anne, and Tom as another example. This set is also in roster notation. We've listed the contents of the set. Another set that's in roster notation might be something like this. C is equal to the set that contains the values 1, 2, 3, 4, 5, and so on and so forth. We've attempted, although this is an infinite list, we've still listed the contents of the set, albeit there is some pattern that we need to follow, and that's what the 3 dots represent. An ellipse means and follow the pattern that was before. So actually in this case here, well, this actually represents the natural numbers. Another way I might do it is D might be equal to the set that contains the values -3, a half, James, and maybe pi. There's another set. We've just listed its contents. It's an unusual set. I don't know where this would occur in the real world. But now we've just listed the contents. It has cardinality 4 because there's 1, 2, 3, 4 elements in it. But we've listed the contents. That's what's known as roster notation, as opposed to what's known as set builder notation. So our set builder notation allows us to construct sets based off a specification for the sets. The set builder notation has two forms. When we're building the set themselves, let's say the syntax of what it looks like is the set looks something like this, followed by a vertical bar, followed by another curly brace. The contents, the syntax, what the contents look like, is listed in there. So the contents, the type of elements, the elements, and their structure, is usually listed on the left-hand side of the bar, and the condition, or the conditions, that need to be met, that need to be met, that goes in there. Are listed on the right hand side. So for example, I'll do a few examples of set builder notation. Actually, let me go to a new page here. So for example, I might say that A is equal to the set of elements that look like this. They look like single things, the set of x's, such that x is an even natural number. So there you go. It has two parts, and we haven't listed the contents of it, but what we're saying is A is the set of x's, there's people. Let's consider this to be like a nightclub, there's people in the nightclub, but the condition, the bouncer was checking for this condition to be met for these people before you were allowed in the nightclub. And actually, when we look at this here, well, the natural numbers, the naturals, okay, are the numbers 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth, okay? So the only way you can get into A, okay, so A must be the set that contains, well, it contains even natural numbers. So the only even natural numbers are, well, they're 2, 4, 6, 8, and so on and so forth. So A now in roster notation would look like 2, 4, 6, 8, and we continue with the pattern like that, okay? We might say something else. We might say that B is the set of, let's say once again, it's a set of values, set of x's, such that x is an element of, let's say, the integers. Okay, so there we go. Z represents the integers. Okay, and we might say that x is less than 6 and it's greater than -2. Okay, there's another way we could write down a set in set builder notation. So the elements in the set need to meet these conditions. Okay, it needs to be an integer, okay, and the integer must be bigger than 2, bigger than -2, and less than 6. So the only things that can go in here possibly are integers with another condition and another condition associated with them. So let's consider the integers. So the integers are, when roster notation, are things like -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay, there's my integers. I can keep going out in both directions. And B in roster notation, okay, is, okay, who can get in here? Well, you have to be an integer, so you can only be one of these numbers. And you need to be bigger than -2. Okay, so all the numbers that are bigger than -2 are over here. Bigger than -2 are these guys. Okay? But another condition is you must be less than 6. So the things that are less than 6 are over here. Okay? So actually, what we have now is that the set B in roster notation contains the values -1, 0, 1, 2, 3, 4, and 5. Okay, has cardinality 1, 2, 3, 4, 5, 6, 7 has cardinality 7. Let's continue and let's see, can we get any other, let's say, unusual sets? Okay, let's say that we have something like this. Okay, let's say that we have A, B. Let's say C is the set. It's the set of ordered pairs. Okay, so let's say it's a set of x's and y's. Okay, such that x and y are elements of the integers. Okay, and we also have, okay, we also have that x and y, both of them here, are less than or equal to 4 and are bigger than 1. Okay, so I'm just doing this notation here to mean that both of these have to meet these two conditions here. Okay, so once again, let's do the integers. Okay, the values that could be in here, the x's and y's are integers. Let's just say we have -1, 0, 1, 2, 3, 4, 5, 6, and so on and so forth. Okay, so they're integers. Any of these things could be in this set. Okay, but the thing about them is the x's need to be greater than 1. So the possible x's are these x's over here. Okay, actually, possible x's and y's are bigger than 1, so they're them things over here, and they can be less than or equal to 4. So that means they're less than or equal to 4, which means they must be less than 5. So actually what we end up with is something like this. Okay, so they're the possible candidates. Yeah, okay? These things here are the x and y values. Okay, so, well, these are ordered pairs. And ordered pairs we get from a Cartesian product. And we've got another video that does that. Okay, but let's try to construct the ordered pairs. So the x values, I have a video later on that will deal with this. My x's are going to be listed down here. My possible x values are down here, which is 2, 3, and 4. And my possible y values are listed across here, which are also 2, 3, and 4. And what we're going to do is we're going to pair the x up with the y, the x with the y, the x with the y, to create structures that look like this. So they have an open round brace, the x value goes in first, followed by the y value. Okay, the x value, the y value, the x value, the y value, the x value, the y value, the x value, oh, the y value, the x value, the y value. We have the x value, the y value. We have 4 with 3. Okay, and we have 4 with 4. Okay, so we take these and we put them into the set. So C is the set that contains the ordered pairs 2, 2, 2, 3, 2, 4, okay, 3, 2, okay, 3, 3, 3, 4, 4, 2, 4, 3, and it also contains the ordered pair 4, 4. And that's the set C as specified through this set builder notation. Okay, let's see what else we can do. Let's do one final one, okay? Let's keep it with this ordered pairs scenario, okay? So let's keep this ordered pairs scenario going, okay? Let's say, okay, something like, okay, let's think about this here. Okay, let's say D is the set of ordered pairs x, y, okay, such that, let's say that x and y are elements of the natural numbers, okay? Let's say x and y, okay, are less than 5 and bigger than 1, okay? And let's say we only have the x divides the y. So they're the only things that can go in, okay? So the possible candidates, first of all, are natural numbers. Well, our natural numbers, okay, are 1, 2, 3, 4, 5, 6, and so on and so forth. But the condition about the x's and y's is that they must be bigger than 1. So they must be over here, okay? And the other condition is that they're less than 5, okay? So what we end up with is less than 5 are these things here. So these are my x's and my y's, yeah, okay? Must be in that set here. Okay, we'll come back to this particular thing here, yeah, but let's do the cross product. Let's see what all of these things would look like without this condition, okay? So what we'll do is we'll do our cross product. I'm going to put my x's down here, my y's. My x's are 2, 3, and 4. My y's are also 2, 3, and 4. My ordered pairs are 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. We have 4, 2. We have 4, 3. And we have 4, 4. Okay? They're the possible things that could be in here so far. But we've got another condition. And the other condition is the x value divides the y value. So the x's must divide the y's. Let's see. Okay, let's look at the first order pair. Does 2 divide 2? And when we talk about divides, we mean that it divides with 0 as a remainder. Yeah, 2 does divide 2. So actually, the set D contains the ordered pair 2, 2. What about? Does 2 divide 3? No, it doesn't. Okay, it goes in once with a remainder of 1, so it doesn't divide 3. Does 2 divide 4? It does. It goes in twice. So 2, 4 is in the set. Okay. What about 3, 2? No, 3 doesn't divide 2. What about 3, 3? 3, 3 does. 3 divides 3. Okay. What about 3, 4? No. What about 4, 2? No. Okay. 4, 3? No. 4 doesn't divide 3. Actually, 4 doesn't divide 2. 4 doesn't divide 3. What about 4, 4? Well, 4 does divide 4, so the other possibility here is that 4 divides 4. Okay. So what we now have is we've built in roster form a set of ordered pairs, and the thing about these ordered pairs are they're all natural. Well, they're I suppose they're ordinates, yeah. Okay, the x's and the y's are all natural numbers. The x's and the y's, okay, are bigger than 1 and less than 5. And also the thing about them is the x divides into the y. That's true also. And this here is the set in roster notation. Okay, guys, once again, my name was Jonathan Lambert, or it is Jonathan Lambert, with the National College of Ireland. And this short video dealing with roster and set builder notation, okay, another video as part of my series of videos on set theory. I hope that this video was some way intuitive, and more importantly, I hope it was helpful for you. And thank you for watching.